are the operators we're interested in. And this whole discussion studies the structure, the topological structure of the spectrum of these operators. And so therefore it's good to recall that the spectrum is actually almost surely constant as soon as you fix some ergodic measure. So if you have an ergodic probability measure, then for almost all little omegas with respect to that measure, the spectrum of this operator is equal to the same set. And that's the set we're interested in. Okay. On that almost sure spectrum, you have a probability measure that is defined by averaging the spectral measure of delta 0 with respect to the ergodic measure. Okay, so this density of states measure is the mu average of the spectral measure of delta 0. And its accumulation function, so the weight it assigns to the interval from -infinity to e, is called k of e and defines the function k, which is the IDS, the integrated density of states. All right. So really by this definition here, you can quickly see that the topological support of this measure here is equal to the almost sure spectrum. So in other words, because this is the accumulation function, which grows exactly where the measure lives, and the measure lives on the spectrum, this function grows on the spectrum and is locally constant away from the spectrum. So that gives us gap labeling. So the gap labels arise because the values of k in gaps are constant, but because between different gaps you have some spectrum, these constant values will be different in different gaps. So you have a one-to-one correspondence between the values of k in a gap and the gap. All right, so gap labeling is about, first of all, assigning these labels and then understanding the numbers that you see. And so this is what I want to explain in these lectures. And the approach that I'm presenting here is due to Johnson. And it really starts with characterizing the points in gaps, the energies that are outside the almost sure spectrum, via an exponential dichotomy. So I don't recall the full definition. It really just means that you have these continuous maps from omega to the real projective line. They're continuous. They're invariant. So, well, if you map by t, then you go from the value of this or this at omega to the image of that line under the cocycle, the transfer matrix at that point. So that I didn't write down, but was discussed yesterday. All right, so the task is to generate a countable subgroup of R that contains all the possible gap labels. And so the question is, how does this subgroup arise? And the answer is, the first step is you have to pass to this mapping torus. So the picture was, I wanted to recall, so you have your space omega here, and the map T just maps a little omega and omega to its image, which is T omega. So if you have an omega here, then T maps it to T omega. So this is done in one time step. This is a discrete dynamical system. The suspension wants to turn that into a continuous time flow. And so it attaches this unit interval here. Okay. And so after one time step, you really want to go from here to here. But in between, what you do is you just flow with unit speed vertically. And then, of course, you end up here. But at time one, you also want to be here. So you identify these 2 points. So that's the construction of this object here. So x is omega across the unit interval, and then you identify these 2 points. So this is now a new topological space, and eventually we want to, not eventually, actually right away, we want to consider continuous functions from that space into the circle. Okay, so we take such a function, phi. It's a continuous map from this guy here, from x to t, and now we plug in that flow. Okay, so now as a function of t, this is a function from R, this is where t lives, into t. Okay, and now you have a function from R to the circle, and that you can lift to a function from R to R, and the lift will be denoted by this tilde here. This is a function from R to R, and for that you ask sort of with which average slope it grows as t goes to infinity. And then you can show that this limit here exists, and in fact, almost surely, so this is just the ergodic theorem, and then is almost surely equal to the same value, and that value is what you're talking about. So this is the number that you assign to that phi, and then you note that the numbers that you get really only take countably many values. Why? Because you can show that this limit is the same for all phi primes that are homotopic to phi. And so therefore, really, this number that you associate with phi, you can really associate with its homotopy class. Okay, and so this is why you then pass to the set of homotopy classes, C#, and that now is the countable object. And for each homotopy class, you can assign this limit here. You can call it a rotation number if you want. And this map now is called the Schwarzmann homomorphism. So this is how far we got yesterday. But it's, so again, it's a simple exercise to show that this object is countable. So the range will also be countable, and it's the range that gives you the gap labels. So that's the content of this gap labeling theorem in the version that Russell Johnson presented in 1986. So you take the Schwarzmann homomorphism and apply it to all homotopy classes. So you look at its range. So this is sometimes called the Schwarzmann group. Maybe I'll just use that terminology. So the Schwarzmann group is the range of the Schwarzmann homomorphism, and it's a countable subgroup of R. Okay, so as such, it's a bunch of real numbers, and these real numbers are the ones that we were after. So the statement is the following. So you first determine the Schwarzmann group, and then you can claim and prove that for every continuous sampling function, remember the f is the guy that generates your potential. So for any sampling function that generates a potential over your fixed base dynamics, you can look at the associated almost sure spectrum, look at an energy outside of it in R, so in a gap, and look at the integrated density of states at that point. So this is the value of the IDS in the gap that E belongs to. And so this value, of course, has to belong to 0, 1, because K is the accumulation function of a probability measure. So it's a non-decreasing function that goes from 0 to 1. So all the values are in 0, 1. So this is not a surprise. It just has to be there. But the question is, what other obstructions are there? And the answer is, well, they have to belong to the Schwarzmann group. That's it. Okay, so again, I want to emphasize one more time that it's true, of course, that the gaps themselves are countable, but as soon as you start varying f over all continuous functions, it's absolutely not clear that one countable set is enough to describe all the values, but it's true.
If the Schwarzmann group is Z, then
yes. Yes.
That argument fails if mu is being a probability measure, finite volume measure, right?
Yes.
Can we have gaps in that case, or is there another?
Oh, you're talking about the continuum case now. Oh, I see.
Let's say it has like volume, you have a mu with volume 10. Can you have gaps even if the Schwarzmann homomorphism is Schwarzmann group is Z in that case, or is there another obstruction that doesn't rely on this basic? It has to go from 0 to 1.
So the question is, what is your mu? Because the way I introduced mu is the mu. Oh, I see. So wait. So mu, do you take a non-normalized? Okay, but you can, if it's, so you're talking about infinite measures now, because if it's finite, you just normalize and then you run the same argument. So if it's infinite, so, okay, so, okay, good point. So yeah, so of course, okay, so I should actually emphasize that Johnson's paper, if you look at it, really focuses on the continuum case. And so this really, in some sense, is sort of a crucial property of the discrete case. I admit that. But yeah, so I guess the answer to your question is the theorem is still true, and you just get rid of the 0, 1 here. Yeah, so no, I mean, the whole point, and I hope I will make this clear in the discussion of the proof, is that as soon as you're outside the spectrum, you have these continuous maps that provide the stable and unstable sections, and those you interpolate suitably to generate, after you pass to their homotopy class, an element in C#, to which you can apply the Schwarzmann homomorphism. And therefore, when you then look at the value of the Schwarzmann homomorphism, you have to be in A. That's really the end of the story. Right? This intersect with a 0, 1 here indeed only comes from the fact that K runs from 0 to 1. Yes. Does it answer your question? You'll ask again, okay. That's fine. Okay, so but still, I mean, yeah. So I will stay in the discrete case for this discussion. So let me try to explain how it follows. But I think it's almost well evident, I hope, because I've introduced all the ingredients, and you just have to put them together. All right. So you take a sampling function and you take a gap or an energy in a gap. And as I just said, so this gap labeling theorem is in the 86 paper, but what's also in the 86 paper is what people call Johnson's theorem. And so really, the gap labeling theorem should be viewed as a corollary to Johnson's theorem. And Johnson's theorem says that outside the spectrum, we have these unstable and stable sections. And so we have them. So this is what Johnson's theorem says. We have an exponential dichotomy that produces these continuous maps into the into RP1. And so we take one of them. And so what we want to do is we want to apply the Schwarzmann homomorphism to them. So there's one problem. So these stable and unstable sections are defined on omega, but the Schwarzmann homomorphism is defined on X, the suspension of omega. So we currently can't apply the Schwarzmann homomorphism to the stable section. So we have to suspend that one too. That's really the thing. Okay, so all right, so our goal is to start with a stable or unstable section and to associate an element of C# of X to T. And we currently don't have that. So we need to interpolate. And so the way we do that is also almost self-evident, but let's still make it explicit. So for that, let's recall how the transfer matrices are defined. So, I mean, you've all seen this countless times during these 2 weeks. So these are the transfer matrices. So let me just emphasize, even though it's obvious. So what happens here is that you form this product. So, and for n, you have n factors. And if you want to pass from n to n plus 1, you just keep what you have and you multiply on the left by the next factor, which would then have an n plus 1 here. Right, so as you go from n to n plus 1, you multiply from the left by a matrix of this form. Okay, and so this is the one-step transition from one matrix product to the next, and we want to make that continuous. So we have to continuously run from this product of n factors to the product of n plus 1 factors, right? So the time interval will be 0, 1. At time 0, we're here, and at time 1, we want to end up at the product that also has the n plus 1 factor here. So in other words, at n, we have the product of this product here with the identity. And at n plus 1, we have the product of this product here with the next one-step transfer matrix. So really what we have to do is we have to run from time 0 to time 1 from the identity to the next factor. That's what we have to do. So that's what the next slide does. So let me just show you the whole thing. This is the homotopy that does it. Right? So you want to run from 0 to 1. That's what you do. So if you are at 0, then this theta will be 0. And you have cosine of 0, minus sine 0, sine 0, cosine 0. That's the identity. You're good. At t equal to 0, you have the identity. What do you have for t equal to 1? For t equal to 1, lambda is 1. Lambda is 1. This is exactly the next guy. Okay? So, I mean, the next guy will be, okay, so this is with t and I need n plus 1, but this will be fixed here. Okay, so this really takes the correct values at 0 and 1. And then by choice of these functions, it's also continuous. You can even make it smooth. So really what you do is you start at the identity at 0, then you rotate to, the thing at pi over 2 here, between time 0 and time 1/2. And once you're there, what you have produced is 0, negative 1, 1, 0. And now you turn the 0 that you have here at time 1/2 into this non-zero guy by letting lambda run from 0 to 1. That's it. So it's a very simple choice of a homotopy that you multiply your n product with from the left, and that produces exactly what you want at n plus 1, and is continuous in between, and everything is great. All right. So remember that these stable and unstable sections are, yes? No, it just is important that you can connect the two things. In principle, yes. So there's one property that I do need. That's what's called monotonicity, but that is baked into the construction. But anything that behaves in a suitable monotonic way is good. Not really.
Go from one to the other by turning the lambda and the theta
Sure.
at the same time.
No, I mean, it's right. I mean, you have 1, 0, 0, 1, and you want to end up with star negative 1, 1, 0, right? So, I mean, what's the most canonical way of doing that? I'm not sure. Of course, there are other ways, but really what you're saying here, this is rotation by 0. Without the star, it's rotation by pi over 2, so I move there. And then I have the rotation with a 0 here, and then I move from the 0 to the star. So I don't know. I mean, I think it's natural. There may be other ways that you prefer. But then there is a property of this particular homotopy that's used in the proof that I'll point out. Yeah, so no, the specific choice of the functions is not important, but definitely you do want to connect the identity and the one-step transfer matrix. Okay, so this is good. So now this ATE omega is sort of a continuous extension of the sequence of matrices here. And so my sections were invariant under these guys. And so really by construction, I can now interpolate the sections so that they remain invariant by just applying these interpolating matrices. So that's really also part of the construction. So that's what happens here. So now I'm actually writing down what it means to be a stable and unstable section. So this means that they are invariant and you have these suitable decay properties either in forward time or in backward time for vectors in those lines. And so this is why we did what we just did. Our continuous time interpolation of the base dynamics and the co-cycle extend these invariant sections to analogous maps that are now defined on X, right? Before they were defined on omega with our continuous interpolation, we extend the definition from here to the entire product. Okay, so now we can think of these stable and unstable sections as continuous functions on the suspension. And so they map into RP1. But I want to have a map from X into T. And now you say, well, RP1 and T are the same thing. Does everyone agree? Okay, thank you. So both are circles. Okay, so there you go. So we have these continuous maps into RP1. We identify RP1 and T. And so these interpolations here, we can now view as elements of CXT. And therefore, they define a class in C#. And we can then apply the Schwarzmann homomorphism. Oh, absolutely. We will see many, many examples. Yeah, so I hope I will have enough time. So I want to do one trivial example and one really not so trivial example. And already in the trivial example, of course, you will see different things that are not homotopic. Okay. So, all right. So the invariance property, and this is the monotonicity property that I was alluding to before. So the stable section is invariant, which means that if I have a 2 vector that defines a line in R2 and apply the transfer matrix to it, I get a new 2 vector that has 2 interpretations. One is by the invariance, it's the stable guy at T omega, but by the fact that I applied the transfer matrix to this 2 vector, it's the shifted 2 vector, right? UN minus 1 UN is mapped to UN plus 1. That's just a defining property of the transfer matrix. Okay, so in other words, what I'm doing here as I sort of iterate either N or T is really I'm running through the sequence of directions or 2 vectors that correspond to actual solutions U of my difference equation. Okay, and so therefore, that's exactly the picture that I drew yesterday, right? In the 2 plane, if I note UN plus 1 as a point in that plane, and then increase N by 1, I get a new point. And so the points that I get here, along with our suitable continuous interpolations, correspond exactly to the rotation of the interpolated solution in that plane. And so the rotation number that the Schwarzmann homomorphism actually measures is exactly the rotation number that you associate with a solution at that energy. And oscillation theory tells you that these oscillations, which of course are, right, if you view things in RP1, then intersecting the x-axis is actually equivalent to having a 0. So counting rotations is the same as counting zeros of solutions, and oscillation theory says counting zeros of solutions is the same as counting eigenvalues. And so this non-essential adjustment is something that I briefly mentioned yesterday. So who was that, Omar or something? Because people generally don't put the minus in front of the Laplacian in the discrete case, for oscillation theory here, we have to count the eigenvalues above E, even though for the IDS we count below. So this is the non-essential adjustment. So if we had actually worked with your normalization, we would not have to make an adjustment here, but here we have to basically flip. So what we're counting here is not really K of E, it's 1 minus K of E, okay? And why is that not a problem? That actually should be an exercise, but it's the end of the 2-week summer school and everybody's tired. Okay, but let me give you an exercise. You can think about it, and then in the examples, you will see it's true. And then after seeing the examples, you can ask yourself, why is it actually true? So here's a claim. The Schwarzmann group always contains Z. That's my claim. Think about it, and you will see in the examples it's true, and it's always true. And because of that, if 1 minus K of E is in the Schwarzmann group, then K of E is also in the Schwarzmann group because it's a group and one is in Z. Okay, so this adjustment that you have to make is non-essential precisely because 1 minus something doesn't change the fact whether or not you're in the Schwarzmann group. All right, so that's it. So oscillation theory connects this rotation of solutions to eigenvalue counting. This 1 minus K of E energy inversion is non-essential, and therefore we can conclude that K of E actually is in the Schwarzmann group. That's it. So again, so the short version of the proof is Johnson tells you outside the spectrum you have these continuous sections. You can suitably interpolate them, retaining the interpretation of what you're doing is describing solutions of the difference equation. And then the rotation of them by oscillation theory is eigenvalue counting, and eigenvalue counting is IDS. End of proof. All right, so this is why Johnson's proof of the gap labeling theorem is relatively simple once you have Johnson's theorem giving you these continuous sections. And I think I remember that someone said that Jake discussed Johnson's theorem. So we're good. So here's the theorem one more time. So the rest of the time I want to use to discuss examples. Okay, so what do we have to do to discuss examples? We have to compute A. A is the range of the Schwarzmann homomorphism. It's a Schwarzmann group. So we want to choose some omega t mu and compute A. That's what we want to do. And the simplest case, of course, is the periodic case. So we'll start with that. And so for that, what do we have to do? So we fix our base. And then we have to look at continuous functions on the suspension and then understand their homotopy classes. So all the examples that we'll look at will be exactly discussed in this way. So we take our omega t, we look at the suspension, try to understand what it looks like. Then we take an arbitrary continuous function on the suspension that takes values in the circle and try to ask ourselves, what is a good representative for its homotopy class? And once we have found a good representative for its homotopy class, we then evaluate this rotation number on that representative. So those will be chosen where this limit of the lift divided by t is easy to identify. Okay, so this here says periodic potentials, example 1. So periodic potentials, remember we're in one space dimension. Those are maps from Z to R, where for some natural number P, shifting n by P doesn't change the values. So this is a P periodic potential. A P periodic potential fits into our framework for suitable choices of omega and T. So omega here is Z mod P times Z, or ZP. And the map is the +1 map, right? So your representatives in ZP are 0 through P minus 1. You keep adding 1, but once you are at P minus 1, adding 1 gives you P, which is equivalent to 0. And you're back, and then you cycle through these P elements. And so therefore, if you iterate your +1 map and you have repetition after P iterations, applying F to it will produce a P periodic potential. And conversely, any p-periodic potential is realized in this framework by a suitable choice of f, because if it's p-periodic, you just have to choose these p-values, and those are exactly the values that you need to determine your function f on this p-element set. Okay, so this is periodic potentials in our framework. Okay, so then we have omega, we have t. For the measure, we have no choice. It has to be the measure, well, it has to be a probability measure, but really it has to assign 1/p to each element. If you don't do that, it's not invariant. All right. So here's the theorem or proposition. So the Schwarzman group for this example, see, because the measure is unique, I don't specify it here, is 1/p times z. So again, this shouldn't surprise anyone because you know periodic potentials and you know that the spectra are unions of p intervals that may or may not touch. So you have up to p-1 gaps. And I don't know if this was covered, but it's true. The density of states measure assigns weight 1/p to each of the bands. So in other words, once you collect the first so many bands, the value of the IDS to the right of it, so in the next gap, will be some integer multiple of 1/p. So this really should be the answer, but let's see how it arises when we compute A. Okay, so let's first look at the suspension. What is the suspension? So we have p points. Oh, let's do it here. So we have p points. Okay, here p is 4. And then we flow from here to 1. And then we immediately go here. So immediately we go here, and then we flow, and we here, and then we go here. Okay, so that's what we do. And this is a circle too. Okay, so X here is a circle. And you can actually identify it with this normalized circle. If you, it's a circle of length p, obviously, if you divide by p. Okay, so this is what X is. And now, after sort of thinking about X as t, continuous functions from X to t, you can think of as continuous functions from t to t. And then you invoke a known result that a continuous function from t to t is homotopic to multiplication by an integer. Okay. So in other words, in the original variables now, really what you do here is you multiply this guy by n. And so, okay, so here if my k is 0, then this portion here is gone. You have t/p times n that's suitably chosen for my continuous function that I have. And that's what it is. And of course, once you know what this function does on pairs 0 and t, then you know it for all because, well, by definition of the suspended dynamics, you run through all the points like that. Anyway, so what I'm saying is the following. So the first step is to look at the suspension, understand what it looks like, answer circle. Then you look at a continuous function on the suspension and ask yourself, what is representative for its homotopy class? Here you go. In these variables, looks like this. Once you have that, the next step is to lift it, divide by t, and send t to infinity. Okay, how do you lift this function? Well, it's very easy to lift it. Here you go. So here's your function. If you want to lift this t-valued function to an r-valued function, it actually has the same form. Once you have this form, you divide by t, and you're left with n/p. Okay. So to answer your question, I mean, already here in this description, you just take two different n's and take two functions of that, and they are not homotopic. So here it's very explicit. Oh, and by the way, I wanted to also point out every time I get to that point, right? So the homework problem that you have is to understand why Z is always a subgroup of the Schwarzman group. But let me just emphasize here, Z is really here. Z is there. Okay, all right. So that was the trivial example. Let's now go to a preview of the more difficult example. So this here says example 2, quasi-periodic potentials, but I'll actually first state what we have for quasi-periodic potentials, but really discuss them in the more general framework in a second. But what is a quasi-periodic potential? Actually, with this audience, I don't have to explain that. Okay. So, but yeah, so, all right. A quasi-periodic potential is generated by a shift on a finite dimensional torus. In some sense, you may or should also assume that the shift is minimal. So that's really what I mean here. And to be more precise, 1 in alpha has to be rationally independent. You know what I mean. Okay, so you have a minimal translation on a d-dimensional torus. That's your base dynamical system. And again, you have no choice for mu, but to take Lebesgue measure. So the unique ergodic measure here is normalized Lebesgue measure on TD. And so therefore, I'm not making mu explicit because that's what it has to be. So we're interested in the Schwarzman group for shift by alpha on the d-dimensional torus. And the answer is that it's z plus alpha zd. And again, z is there. Okay, so it's, and of course, you may know this very well. I don't know by which methods, but probably maybe by this one. So I will just flash this here, but I will not actually discuss it because I'll do it in a more general setting on the next slide. But again, the strategy is the same. So you take your omega, which is TD, you have your transformation T alpha, you ask yourself, what does the suspension look like? Answer, it's a T plus 1 dimensional torus. And then you look at continuous functions from that object into the circle and ask yourself if they have representatives for their homotopy classes. And answer is, again, it's characters, just as in the previous case. And then once you have these characters, you plug in the continuous time dynamics and compute the rotation number. So this calculation then shows you that you will be in here and everything that you have in the set actually is attained. It does work, yes? Yes, it does. What do you mean, sorry? Oh, no, I don't think I... So no, I think what I was referring to is the K-theory approach to gap labeling. And really what I said is I've only seen the K-theory discussion for the case D equal to 1. I'm not claiming that it doesn't exist for larger values of D, but just the paper, I mean, it's Pimsner, Voiculescu and Riefel and these people, they've computed the K0 group of the rotation algebra, but that's really for the case D equal to 1 here. But I'm sure that if you ask the experts in that area, they will tell you how to do the higher D case. Yeah, so, right. No, I'm not claiming it doesn't work for large Ds. I'm just saying that there were some K-theory papers that focused on the case D equal to 1, and here is the Johnson approach to the case of general D. All right, so here's the general setting. So it's, well, it's example 3 and says affine torus maps. And the theorem is the following. So you take an SLDZ matrix and you take an element of TD and you look at this affine map. So omega, an element of TD, is mapped to A omega plus B. So that's an affine map. So it's a linear map composed with a translation. All right. So you assume that this map has an ergodic measure that has full support. Okay, so this will be true in the applications that I'll discuss in a moment. Then the theorem identifies the Schwarzman group as this set. And again, Z is here, right? You have all the N's in Z here. But what you also have are these K comma B's, where B is the translation vector here, and K runs through all integer entried elements of the kernel of I minus A star. So that's what the Schwarzman group is equal to. So you see here, if A is equal to 1, you just get omega gets mapped to omega shifted by B, and that is the shift on the D torus. And as before, if you're rationally independent, then you do have Lebesgue measure that is ergodic and fully supported. So you recover the previous result. Now you have these two parts. You have the elements of Z and you have these guys here. But these guys here, you only have if you actually have a non-trivial kernel. If the kernel is trivial, then you add 0 to the ends. So in other words, if 1 is not an eigenvalue of A, then the only K that's in here is the 0 K. and this is 0, and really the Schwarzman group consists of all n's in Z. Okay, so if 1 is not an eigenvalue of A, then the Schwarzman group is equal to Z. But if the Schwarzman group is equal to Z, as was mentioned yesterday, gap labeling tells you that there can be no gap with a rotation number strictly between 0 and 1, but you would have such a gap if you had an interior gap. So you don't have any interior gaps, so the spectrum is connected. All right, so you may say, well, does this ever occur? No, no, because Johnson's theorem tells you that if you're not in the spectrum, you have these dichotomies, and then you can run the argument. So if they touch, there is no energy in that gap to which you can associate these. Yeah, so it just doesn't work. So it gives you no statement there. Ah, okay, so that's okay, let me go there. It's good to clarify that. So let me actually go to the gap labeling theorem. Okay, so what does the gap labeling theorem actually say? So it tells you, take your base dynamics and compute the Schwarzman group. Once you have the Schwarzman group, you know what this set is. And the gap labeling theorem tells you that for every sampling function and for every gap, the IDS takes values in that set. It absolutely does not tell you that each value here will be taken on some gap. This is just a countable set that contains all values of this form. It may be too large, right? I'm not saying they're equal. I'm not saying that if I go through all the gaps. Yes, exactly. So of course, P minus 1 open gaps, yes. Right. So therefore, the periodic case is, I mean, I will discuss it if I have time in a moment. No, but so first of all, this is an inclusion, right? If you take all gaps and take the union of all gaps over all sampling functions, and you get a bunch of numbers, and these numbers are contained in A intersected 0, 1. That's a statement. But is it equal? Right? It's not clear in general. However, for the periodic case, it is clear because we know the values and gaps must be of the form integer divided by P. And some periodic potentials in one dimensions do have P minus 1 gaps. And so therefore, it's an equality, right? So these interior gaps, they're only P minus 1 many. And so there are cases where all of them are taken. And that means that the labeled set, this set here, is minimal. It's not too big. So it's each element on the right-hand side is necessary for some choice of sampling function and some energy in the, right? No, but in general, this is a very important question that doesn't always have an answer. Is the label set minimal? Okay, so it's not completely understood. Okay, so I just made the observation that if a 1 is not an eigenvalue of A, then the Schwarzman group is Z, and for every continuous sampling function, the spectrum is an interval for every F. Okay, so then here's of course an example that makes this that makes you see that first of all, this is not a vacuous statement, and second of all, an example where it occurs is actually interesting, namely the cat map is a well-known map. So the cat map is given by A equal to 2, 1, 1, 1. That's the matrix you put here. D is equal to 2, and B is just 0. So that's Arnold's cat map. And now you compute the eigenvalues of A, and you will see that 1 is not an eigenvalue. And therefore, it's also not an eigenvalue of A star, which is equal to A. Okay. Yeah, exactly. So okay, sorry. So yes and yes. So first of all, the cat map is that, so you have to take these things, but you're right. I mean, you don't even have to compute this if this is already not there. But you're also right, you can just take a non-zero B, and now everybody's happy. Okay, anyway, so this really is the cat map that is well studied, and the previous two remarks apply to this example. And we see that all Schrödinger operators defined by the cat map have no gaps in their spectrum. Okay, so for the skew shift, another well-studied example, it's these choices. So A, so again, B is equal to 2, A is 1, 0, 1, 1, and B is alpha 0, and alpha is irrational, right? So what you do here in the first component is you take the first omega plus alpha, so you rotate in one component, And in the other component, you take the sum of the two entries of the omega. So it's omega 1 plus alpha and omega 1 plus omega 2. That's the map with alpha irrational. Okay, so now we do our little computation. So A star is 1101, which does have 1 as an eigenvalue, and the eigenvectors are multiples of 1, 0. Okay, the matrix is 1, 1, 0, 1, and the eigenvectors corresponding to eigenvalue 1 are multiples of 1, 0. I'm interested in those with integer entries. So the vectors in question are integer and 0. And now I have to take this inner product of integer and 0 with alpha and 0. So I get integer and times alpha. Okay, so I get the z from here. And when I compute this, my little discussion tells us this is exactly alpha z. So this is the label set for this Q shift. Okay, so I think I will try to finish in time. So which means that I will maybe abbreviate a few things here and there, but I do want to discuss how this theorem is proved. So again, the strategy is the same. So you have your base dynamics, you suspend, and then on the suspension, you look at continuous maps into the circle, and then you try to find representatives of the homotopy class. And once you have found them, then you evaluate the rotation number using those suitably chosen representatives. So the first lemma is about choosing the representative, and the next lemma will be about evaluation of the rotation number, even though, I mean, you can already see that. So these will be my representatives. You can sort of see how you lift. And once you lift and divide by t, you see what you get, obviously. Okay, so that's how it goes. All right, so you take the suspension and you define this map here. And the map takes the form k omega plus nt plus t times kb. B comes from the map. The k is determined just as discussed before. It's an element of this z d intersected kernel of 1 minus a star. And n is an integer. Okay, so this is how we determine k, n, and b. And with this, you can define a map on the suspension into the circle. And then you want to show that, first of all, this really is a well-defined continuous map. Well-defined, well, this suspension has this identification thing, right? You have the top and the bottom that are sort of glued together after twisting with the dynamics. So the function has to respect that. So you check that that actually works. And so for that, you actually need this property, as we'll see in a moment. So therefore, these are continuous maps from xb to t. And then this is really the crucial property. Well, this is the crucial property. You first do it for b equal to 0 and then somehow move from 0 to b. Okay, so let's discuss the case b equal to 0 first. You take any continuous function from x0 to t, and you have to show that there is a k and k and an n and z, so that this continuous function that you start with is homotopic to this object here. So you can use them as representatives for all homotopy classes. So you do this first for b equal to 0, and then you somehow relate x0 and xb, and therefore get the resulting statement for the general case. So those are the 4 steps that allow you to later look at rotation numbers evaluated, along these guys. Okay, so the first thing is that the identification of top and bottom is such that G plays well with it. So you assume that K is in this kernel. This means that A star K is K. And this is exactly used to relate what you have after shifting in time by 1 with the map. Okay, so you need this to be equal to that to say that you're well defined, because this is how you identify top and bottom in the suspension. Okay, so maybe here's where I save some time. So you write down what this is, you write down what this is, and then you rewrite a little bit. And then the crucial property really here is that, if you rewrite here by bringing A to the other side in the inner product, what you really need is these guys to be equal. So once you sort of write down this and you write down this, these guys being equal tells you that you're really looking at such case. This is where it comes from. Okay, so that's the first thing. The second thing is, okay, so you start with a general continuous function and you somehow have to show that it's homotopic to one of these guys. Okay, so let me draw my picture one more time. So we have omega is TD and we have 0, 1 here. Okay. So now, so this is my X. And again, top and bottom are identified in the way discussed many times. So what I want to do is I want to look at these slices here. This is what is denoted by omega t. And of course, each TD times a fixed little t is, of course, basically the same as TD, right? So each of these slices are basically TDs. So if I have a continuous function on all of X, it's certainly continuous on each of these slices. And as a continuous function on TD, it will be homotopic to a character. Okay, so this is what I want to do. So I have all these slices here, and I restrict my continuous function on the whole thing to a slice, invoke the statement that it's homotopic to a character, and then I have all these characters correspond or indexed by t. But then, since the whole thing is continuous, that character has to vary continuously with t, and therefore has to be constant. Okay, so that's how you choose your k. Okay, so I don't know where that says it there. Okay, there you go. So you take the slices, you find a character to which it's homotopic, but then the character has to vary homotopically. And so therefore it's the same k for all, and this is how you choose k. Okay, so you have your continuous function on the whole thing, and there's one k, and you can find it after homotomizing any slice here to a character. That will be the k that you use. Okay, so now, what am I saying here? Okay, right. So we have found this k that works for all slices. And now, I have at the bottom here, I have the character that corresponds to the bottom row. And at the top row, sorry, no, so at the top, what am I talking about? So the, so remember that you go from omega 1 to a omega. So remember b is equal to 0. Our map t is just multiplication by a. Okay, so I have this slice and I have this slice, but there's this map a. And so therefore, by identification of these two things, I have two descriptions for the character that I can use for the bottom slice, namely the one that I have, k omega. And I also have the one that comes from here with the same k, but then it corresponds to a omega. And so therefore, the two have to be equal. Okay, so, right, so this guy has to be equal to that guy for the k that was found here, and therefore I get this equality. Okay, so the k that was identified in the first step has to be in that kernel I minus a star. So this is how we find the little k. And so now, so this was for this slice, and now I look at this slice. Okay, what happens there? So I look at the points 0, t, and so I observe that it's a circle. Why? Okay, so I start here, I move up, and then as I flip back down, I have to go to the image of this point. But the image of 0 under multiplication with a is 0. So therefore, this point is identified with that point, and so therefore, this object here is a circle. Okay, and now I do the same thing. I have this continuous function on the whole thing restricted to a continuous function on this circle. That circle is such that continuous functions on it are homotopic, again, to a character. And so this is where the n comes from. Okay, so there exists an n, so that this map here is homotopic to multiplication by n. And so now I found k and n. And so now I pass, well, basically I want to say this is it. And how do I argue? So I can take my function here. I know how to deform it continuously to turn it into a character here, namely this kx. And I know how to deform it continuously to turn it into n times t there. And there is, again, this is a lemma from homotopy theory. This extends to a homotopy on the whole thing. So there is a homotopic element that actually has these linearizations, if you want, on the left and on the bottom. Okay, and remember, these things are identified. And so because of that, if you now subtract it off, then you get 0 on these boundary parts. So this difference here will be 0 on these two guys on the boundary. And so then another lemma from homotopy discussions is that now you're homotopic to the 0 function. Okay, so the first thing was to move from your original map G to one that we call H. So H is homotopic to G. And then H, by this discussion, is homotopic to GKN for KN as chosen on the previous slide. And this shows that the G we started with has the GKN with those K and N's as chosen above in its homotopy class. And so this is this discussion for B equal to 1. And so now I will just very quickly flash that there's a way of relating x0 to xb. So there's a homeomorphism between these two mapping tori. And then you can compose with this homeomorphism. You already understand how to look at the homotopy classes for one, and then you get it for the other one. It's a very explicit map. And with this map, you can then compose the GKN zeros that you found in part B with this homeomorphism to find the representatives for XB. Okay, so anyway, the short version is you have homotopy to characters for tori and circle. And once you force sort of these linearizations on the boundary and subtract it off, then what's left is non-homotopic. So the whole thing can be in homotopy with this function in question. So that's the first step. The second step is to take such a function and to compute its rotation number. And so this now is as trivial as it was in the previous case. So the function takes this form. And so once you have this description, it's sort of clear how to lift it so that it takes values in R, namely just read it like that, but regard it as an element in R. I mean, it's just how the projection from R to T works. But once you have that, you can divide by T, and this goes away, and you get n plus kb, and that's the answer. Okay, so this shows that every rotation number is in the set on the right-hand side, but it also shows that everything on the right-hand side is a rotation number because you just choose that G, K, N, B, and it has that rotation number. So it's really an equality of the two sides. Okay, good. So this follows from the two lemmas. So I still have a few minutes, right? Okay, good. So good. So at this point, what we have seen is that we have a gap labeling theorem that really comes out of Johnson's theorem producing these stable and unstable sections. And we have discussed the periodic case and affine torus maps, which also includes quasi-periodic guys, the cat map, and the skew shift. And all these arguments are relatively elementary and produce some surprising observations. For example, whenever you have these affine torus maps where the right-hand side just collapses to Z, the conclusion is that you have no gaps in your spectrum for any sampling function. Okay, so now the next, well, the last part is this discussion of whether some gap labels actually don't occur because gaps close. So, okay, so for the periodic case, I mean, as already discussed, we saw that, well, you have you have 1 over p times z. And so you have p minus 1 elements that lie strictly between 0 and 1. So you can have at most p minus 1 bounded gaps. And it's well known that there are examples with p minus 1 interior / bounded gaps. Okay, but more is known. In fact, it's well known that this openness of all gaps is a generic phenomenon. Okay, so for any period p, there is a dense open set. I mean, this, of course, you cannot take too seriously. So these are the continuous functions on this finite set. So it's really all functions that are R-valued. So it's really R to the p, such that for every choice in this dense open set, the associated spectrum indeed has p minus 1 interior gaps. Okay, so not only does it happen sometimes, it happens generically. Okay, so let's see. I don't know if I should prove that. The proof is one slide. So let me tell you that the slide is here. And if there's any question at the end about the slide and people don't leave the room, then I will look at that slide one more time. So I just want to summarize what we did. So, so this generic openness of all gaps is a classical result. But again, so as I pointed out when you asked the question, in general, it's just not understood. So one question is, I compute my label set, which is Schwarzmann group intersected with the interval 0, 1. I get a set. And one question is it too big, or is it actually true that if I take the union over all values of the IDS and gaps, unioned over all sampling functions, I actually get that set? Okay, so that's the first question. Are there non-essential elements in that set on the right, or is everyone taken for some example? And therefore, it's a minimal choice of gap labels. So this is in general not known. That's the first question. In cases where the answer is yes, it is a minimal set, the answer is always stronger than just saying there exists a sampling function so that for its spectrum, there exists a gap so that k in that gap takes the value that you're interested in, right? This is the answer in a positive sense to that question, but whenever you have a positive answer, the answer is stronger. It doesn't say there exists a sampling function, always says there is a dense G delta set of sampling functions. So this is basically the currently best known result. And I'm really interested in seeing more results along these lines, but it's a difficult problem. So what is the result? So basically what I just said, you take a label, okay, so you compute the Schwarzmann group for your base dynamics, intersect it with 0, 1. The elements are the possible gap labels. And so the question is that gap label actually the value of the IDS in the gap? And the answer is, well, for every such label, there will be, yes. Sorry, I don't want to confuse you. The answer actually is not as written as here, but it is still true. So for every label, there is a dense open set so that that label is taken on some gap for the sampling functions in this dense open set. And if you want to have sampling functions that have all gaps open, then of course you take the intersection over all else, which remember belong to a countable set. So the theorem here is formulated as an all gaps open result, but the real result is take a gap label, ask how many sampling functions have that as a gap label for its spectrum, and the answer is it's a dense open set. Okay, so this is what you want, and so the question is when can you prove it? And so here's the answer. So omega is a compact metric space. That's our overall assumption. So really here are the restrictive assumptions. So T not merely has to be an ergodic homeomorphism for some choice of mu. In fact, this ergodic measure has to be unique, right? Strictly ergodic means uniquely ergodic and minimal. So there has to be a unique ergodic measure and all orbits are dense. So those are the two assumptions on T. So in our previous discussion, the skew shift is strictly ergodic, the minimal shifts on tori are strictly ergodic, but the cat map is not. So this doesn't cover the cat map. Okay, and so moreover, it has a finite dimensional factor. So you can basically extract by projecting down to a smaller space something that is defined by a finite dimensional space. But all our examples were defined on finite dimensional tori, so there is no need to extract factors here. So again, minimal shifts on tori and skew shifts are covered by this result. And those are the assumptions. And like I said, the theorem really, the appropriate formulation is for every element in the label set, the set of Fs for which this label actually is an honest value on a gap is open and dense. And then if you intersect over these countably many Ls, you get one fixed dense G delta set, so that for every F in this dense G delta set, and every label, you have a gap with that label, meaning all gaps are open. Okay, so that's the result. I will not say anything about the proof. So I've worked with Arthur for a long time, and this I think is the most difficult proof I've ever seen him generate. I mean, that was quite amazing to see that in action. Yeah, so it's one of these papers that I don't think anyone has ever read, except for the authors, of course. But yeah, no, it's what I'm trying to say is it's a very, very difficult proof, but I think the result is really interesting. And I'm really hoping that there will be further developments in that direction. But the problem is anytime I give a talk about gap labeling and I sort of advertise this problem and people say, oh, this sounds really interesting. And then I send them this paper. A week later, they say, oh, actually, I'm busy with other things. So this is what usually happens. All right. So anyway, so let me advertise one more time here. Okay. So, right. So as I said before, so once you have this under these assumptions, the Schwarzman group really is a minimal set of gap labels. For that, you don't need this genericity. You just need one F for which these labels appear. But it's, so this is another thing. So a question, if anyone is interested, it's a summer school. So it's good to propose some problems. So I've mentioned this K-theory gap labeling. And I mean, there are two natural questions to which I don't have the answer. I don't know if anyone does. So the first question is, are the label sets in the two approaches always the same, right? So both gap labeling theorems tell you that the IDS takes value in the respective set that you generate in one of the two ways. Okay, so there are these two sets that you can use as gap labels. So I don't know if they're always the same. I think in the examples that are understood, they are the same, but is it always true that they are the same? If they are not the same, then maybe one of them has these extra labels that are never used, right? And so therefore, this minimality question is independently interesting, but especially when it comes to understanding whether the two are equal, because if they aren't, then one of them really contains things that are not needed for gap labeling. So that's that question. And as I said, this theorem covers shifts and skew shifts on tori. And yesterday I promised I will show the summary slide twice, once before we do the things and once after we do the things. So I'm showing it now just so that you, in your mind, go through the things we talked about and basically check off that, yes, indeed, we talked about each bullet point. Okay, so just as a summary. So the gaps of the almost pure spectrum can be labeled by the constant value of the integrated density of states in that gap. The integrated density of states is defined by eigenvalue counting, and eigenvalue counting is related by oscillation theory to zero counting. And zero counting in terms is related to counting rotations of solutions in this UN plus one plane. So in order to study these rotations appropriately, you can't just look at the sequence of points in that plane. You have to interpolate so that you actually have a curve that never falls into the origin, which it doesn't. And so you interpolate, and we interpolated the base dynamics and the cocycle, the base dynamics yesterday, the cocycle today. And once you do that, then you have these curves. And so following these curves corresponding to solutions, by Johnson's theorem really can be done by using these stable and unstable sections. And so therefore, because Johnson gave you these continuous sections, by interpolating them, we get objects to which we can apply the Schwarzman homomorphism, and the answer is indeed the rotation of the solution, and therefore describes the value of the IDS. So this is how the gap labeling theorem arises, by this connection, Johnson's theorem and oscillation theory. And then once you have this general result, then you compute the Schwarzman group. And we've seen some examples where we just computed it. And as we've seen for some examples, including the cat map, the group is trivial in the sense that it prohibits any interior bounded gaps. And so spectra are connected in that case for all sampling functions. Whereas for other examples, it gives you possible gap labels that are strictly between 0 and 1. Once you have these gap labels, you ask yourself, do I have gaps corresponding to them? And then I showed you some results that are to the effect that yes, there are examples where these gap labels are actual labels for gaps for suitably chosen sampling functions. And in fact, whenever you can do that, the set of sampling functions for which it works is a density delta set, so relatively large. Okay, so with this, I thank you all for coming to these lectures. Actually, before we do anything else, it's customary at the end of an event to thank the organizers. So I invite you to join me in thanking the organizers for putting together this nice school. Yeah, exactly. So that's what I wanted to say. So the first thing that you, oh, it's not even here anymore. Oh, why is it gone? So I somehow killed the assumption. It should have been there. Sorry about that. So it's an overall assumption of Johnson's theorem that, so first of all, you need a topological space, right? You can't just realize it on some abstract measure space. And that topological space is sort of unique because it has to be equal to the topological support of the ergodic measure that you're working with. So in that case, there is no choice. You have to, it's just once you have your dynamics and your ergodic measure, the space is determined. That's the first answer. And the second answer is if you take a different ergodic measure, then things really change. So the Schwarzman homomorphism actually depends on the choice of ergodic measure because the limit that we're talking about, defining the rotation number, is an almost sure limit. And almost surely means outside of a set of measure 0 with respect to the ergodic measure that you're working with. So for a different choice of ergodic measure, you will actually get a different almost sure limit potential. So, okay, can you give me an example? I mean, okay, but this is not really a well-definedness issue, right? What I'm saying is you fix a topology, you fix an ergodic measure that's fully supported, then I do my thing, right? There are no two different ways that, right, that you have to sort of bring together in the end. I mean, so really, right, but if you change the topology, you change the set of continuous sampling functions. Right, so the Schwarzman group labels for all sampling functions, but they are required to be continuous, and that notion changes with the topology. Well, so I don't think it tells you very much. I mean, it is true that with more rank you get more options, but I think the first step is always to answer the question whether you have anything beyond Z, and if you do, whether what you have is dense, and then of course you already, I think, are going up in rank. Oh, sorry. What I mean, so no. What I mean is whether the gaps are dense, right? So as soon as you, that requires more than one rank, right? Okay, so that's true. Okay, so I mean, in some sense, right? You're trying to generalize something where the answer depends on the specifics, right? So if you are rank 1, you are in this situation where, say, you have Z plus alpha Z, but alpha now is forced to be rational. But now you're again in this concrete setting, and you ask yourself whether, okay, so is your question whether you can have a rank 1 situation outside of the periodic case? A finite gap situation outside of the periodic case. Is that the question?
Mostly I was like, no, it's like rank 2 versus rank 3. Does that tell you anything interesting, or is that?
Oh, no. I don't think so. So really, I mean, yes and no. So because the questions that you are able to answer are not that specific that they care about the exact values. I think most of the things that you care about are whether the labels are dense or not. That's really the first question. And there's no new phenomena going from rank 2 to rank 3. But of course, you do have more labels in principle, but what that really tells you, I don't know. I mean, yeah, so I mean, in the periodic case, it's sort of pretty explicit. So I think this was discussed in one of the courses. So if you have an F, then you form this matrix product over one period. So it's a product of P matrices. And then you look at the trace of this matrix. And if that trace So this trace will go up and down, and I'm sure you've seen this picture. And if one of the critical values is exactly ±2, at that point you have a closed gap. So this now you can reinterpret in terms of the p-values. I mean, you can just look at the trace of this object, you impose certain properties, and this just tells you what the values have to be. So it's sort of an implicit problem, but it's relatively explicit. So in this more general situation, I don't think there's any understanding of which Fs are actually bad. But in the periodic case, it's pretty explicit, I would say. No, I mean, basically, as soon as you leave the periodic case, I think the next simplest case is a rational rotation on the circle. And even there, it's a difficult theorem. Right? This is Dry-10-Martini for general continuous sampling functions. It's a difficult problem. Yes and no. So the nice thing about gap labeling is that it tells you not only what the labels and gaps are, but also if you don't have a gap with that label, it tells you precisely where it should be. Because for each sampling function, you have the IDS, and it grows from 0 to 1, and it will take the label value at some energy E. And if there's no gap around it, then you call this a closed gap, right? And so the question is whether you can perturb your sampling function so that a gap opens there. And so this is indeed addressed in the proof. And I mean, there are some intuitive aspects and some technical aspects. But yes, so there are some things that you can look at in the proof that sort of tell you how you should do your perturbation. And in fact, this is part 2 of 2 papers. Part 1 was only about opening gaps by perturbing, but part 2 is about controlling the rotation number of the perturbations. This is what made it so difficult. So we had an earlier paper in 2009 that just says that Cantor spectrum is generic, but you don't worry about keeping the label fixed. You just want to find a dense set of energies in the spectrum where you have this, right? And so therefore, perturbing to turn something that's not yet uniformly hyperbolic into uniformly hyperbolic is easier than doing the same thing while controlling the rotation number. And so this is the very technical aspect here. So it's not addressed. So I don't think there's an obstruction to the aim. So I think one should try. No, so I mean, basically, so let me actually think. Okay, so anyway, so this, like I just said, is about perturbations of SL2R cocycles. If you have a larger range and you have bigger matrices. And so this is sort of a step 3 or 4 in the progression. And the first step in this progression is just Boki's thesis. I don't know if you've ever looked at that. So basically, you want to show that if you're non-uniformly hyperbolic, then you can perturb in C0 to make it have exponent 0. That's sort of his thesis. And so then from that point, there is a progression of steps. So the first thing is to go from non-uniformly hyperbolic to 0 exponents. The next step is to go from 0 exponent by perturbing further to make it bounded. And once you have it bounded, then you perturb one more time to make it uniformly hyperbolic. So it's sort of 3 steps. And so all these things you can in principle discuss for larger cocycles. I'm sure some of these steps have been discussed. I don't know if all of them have been discussed, but again, it's definitely a worthwhile project to undertake. I don't know if anyone has done that yet. Maybe someone is interested. Thank you.